All right, let's decode the world of algorithms. We're going deep into grokking algorithms, a book that tries to make even really complex algorithms approachable and, even fun.
Yeah, algorithms can seem a little intimidating, but this book does a good job of making them engaging.
Yeah, I think so too. So it's basically a crash course in how computers solve problems.
Hmm.
Like, it's your cheat sheet for everything from finding the fastest route somewhere to, sorting tons of data.
Exactly. And it's pretty incredible how these, what seem like simple instructions, can totally revolutionize so much, from online searches to even like artificial intelligence.
Right, yeah, like Chapter 1 starts off by defining what an algorithm actually is. It's basically a set of instructions to complete a task. So it's like a recipe, but for a computer.
Yeah, and like a good recipe, a good algorithm needs to be efficient and accurate.
Right. And that's where stuff like binary search comes in.
Right.
This algorithm is amazing for finding things quickly. Think about like searching for a name in a phone book. We wouldn't go page by page, right?
No way. You probably start in the middle somewhere and keep narrowing it down.
Exactly. Binary search does the same thing, divides the search space in half over and over. It's so much faster than checking each item one by one.
So that's why my computer can find one file out of millions so fast. It's not magic, it's just a clever algorithm.
Right. And the book uses this thing called big O notation to explain how fast an algorithm is. So binary search has what's called logarithmic time, meaning it gets faster proportionally. The problem gets bigger.
Oh, that's cool.
Yeah, it's super cool. They even go this example of a NASA landing module, which had to like calculate its landing spot super quickly in just a few seconds. Talk about high stakes. Speed is definitely key there.
Yeah, absolutely. So we've seen algorithms can be really fast, but how do they store and organize all that data in the first place?
Well, that's where chapter 2 comes in. It introduces two fundamental data structures,
Yeah.
arrays and linked lists. These are like the building blocks for how information is organized in a computer's memory.
Okay, can you break those down a bit more? I'm not sure I totally get the difference between those.
Sure. Think of an array like a set of labeled drawers, right? Each drawer is for a specific thing. So you can find any item really fast because you know exactly where to look.
Oh, that makes sense. But what if you need to add or remove something? Do you have to move everything around?
Exactly. That's one downside of arrays. Adding or removing elements can be uh, inefficient, especially with large data sets. That's where linked lists come in. Imagine like a treasure hunt, where each key leads you to the next one.
Okay, so instead of everything being in order, each item points to the next one.
Precisely, like a chain. Each link has the address of the next one. The book compares it to a restaurant order queue. You can easily add new orders without rearranging the whole list.
So arrays are good for finding things fast, and linked lists are better for adding and removing things.
Yeah, you got it. And there are even hybrid structures that combine both, depending on what you need it for. So chapter 2 also talks about this basic sorting algorithm called selection sort. It's like organizing a music playlist manually, finding the smallest element, putting it first, and then repeating for the rest.
Sounds pretty simple, but I can imagine it would take forever with a giant playlist.
For sure, it's not the best way for big data sets. The book says selection sort has a runtime of ON, which basically means the time it takes grows way faster than the amount of data.
Oof, that's not good.
Yeah, but luckily there are faster algorithms like quicksort, which we'll get into later. But first, get ready for a mind-bending concept in Chapter 3, recursion.
Oh yeah, recursion. Always a little tricky for me. Isn't that where a function calls itself?
That's the one. It can be hard to grasp, but it's powerful for breaking down complex problems into smaller, similar steps. The book uses this analogy: searching for a key in a box full of other boxes. If you find another box, you repeat the same search inside that box.
Okay, I kind of get it. But how does the computer keep track of all these boxes within boxes?
That's where the call stack comes in. Think of it as the computer's short-term memory for functions. Each function called is added to the stack, and when it's done, it's popped off.
So it's like making sure the function doesn't forget where it was.
Exactly. And it prevents infinite recursion, which is basically when a recursive function just keeps calling itself forever.
Oh, that sounds bad.
Yeah, total disaster. The book actually gives some good real-world examples of recursion, like navigating file systems, folders within folders. It's also using some sorting algorithms, which brings us to Chapter 4 and quicksort.
Okay, how does quicksort use recursion to sort things faster than selection sort?
Well, quicksort uses this clever technique called divide and conquer. It breaks the problem down into smaller subproblems, solves them recursively, and combines the solutions.
Divide and conquer, I like that.
Yeah, it's a good one. The book gives this cool example of dividing farmland into the largest possible square plots, which is actually related to an ancient algorithm, Euclid's algorithm.
Whoa, ancient math. This is getting deep.
I know, right? It's cool how algorithms can connect these seemingly unrelated concepts.
So how does the farmland thing relate to quicksort?
So in quicksort, you choose a pivot element and then partition the array around it. Smaller elements go left, larger ones go right. Then you recursively sort the subarrays on each side.
Ah, I see. And because you're always dividing the problem in half, it sorts way faster on average than selection sort.
Exactly. Quicksort has an average runtime of ON log n, which is way better than ON. But it's worth noting that worst case scenario, quicksort can also be ON.
So it's not always the best choice.
It really depends on the data and what you're trying to do. It's like picking the right tool for the job. Sometimes a simple tool like selection sort is enough, but for bigger jobs, you might need something more powerful like quicksort.
Right, makes sense.
And this brings us back to big O notation, which lets us compare the efficiency of different algorithms. The book really emphasizes understanding the trade-offs.
Yeah, I'm starting to see how big O notation gives us a way to talk about efficiency without getting lost in the details.
Exactly. So that leads us to another cool data structure in Chapter 5, hash tables. These are known for being super fast at lookups, insertions, and deletions.
Sounds almost magical. How do they work?
Imagine you have a magic book where you could instantly find the price of any grocery item, without having to search through a list.
I wish I had that at the store.
Right. Well, a hash table is kind of like that. It uses this special function called a hash function to map each key to a specific spot in an array.
So it's like having a designated spot for each item in the store.
Exactly. That's why lookups are super fast. The computer knows exactly where to go to find the information.
But what if two items end up in the same spot?
That's called a collision, and hash tables need to handle them carefully. One way is to use linked lists to store multiple items in the same spot.
Ah, so it's like having multiple items with the same label on a shelf.
You got it. The book stresses having a good hash function that minimizes those collisions and spreads the data evenly.
Makes sense.
And the real-world uses for hash tables are, everywhere. Think about preventing duplicates, like making sure everyone only votes once in an election.
Oh, yeah, you could store voter names in a hash table and instantly check if a name is already there.
Exactly.
Yeah.
Hash tables are also used for caching data, like storing frequently accessed web pages so they load faster.
So every time I visit a website, it might be pulling from a hash table to make things faster.
That's right. Just one example of how they're working behind the scenes to make our digital lives smoother.
They're like little helpers.
I know, right? Now, get ready for Chapter 6, because we're entering the world of graphs. This is a whole new way to model relationships and connections.
Graphs, like the ones from math class.
Kinda, but in computer science, graphs represent things like social networks or transportation systems, or even like connections between neurons in the brain.
Oh, wow. So it's not just plotting points, it's connecting different entities.
Exactly. Each graph has nodes, which are the entities, and edges, the connections between them, like a map where cities are nodes, roads are edges.
Okay, so I can see how that would be useful for finding, like, the shortest route between two cities.
That's where breadth first search, or BFS, comes in. It explores the graph level by level, checking closer connections before moving further out.
Level by level, okay.
Yeah. The book uses the analogy of finding a mango seller in your network. You start with your immediate friends, then their friends, and so on.
So it's like expanding outwards from a central point.
Exactly. BFS uses a data structure called a queue to keep track of the nodes to be explored. Think of it like a line at the grocery store, first in, first out.
Gotcha. So make sure you explore the nodes in the order they were added, which is important for finding the shortest path, right?
Exactly. And the chapter also talks about directed and undirected graphs. Directed graphs have arrows showing a one-way relationship, like Alex owes money to Rama. Undirected graphs are two-way relationships, like Ross and Rachel dated.
Okay, so the direction of the connection makes a big difference.
Huge difference. And lastly, the chapter touches on topological sort, an algorithm that shows dependencies between nodes, like the order you need to do things in your morning routine.
So if putting on shoes depends on putting on socks, topological sort would figure that order out.
Exactly. It's all about the right sequence of actions based on what depends on what.
Wow, this is a lot to take in. I'm starting to get it, though, I think.
That's great, but we're just getting started. Chapter 7 takes our graph knowledge to a whole new level by introducing weighted graphs. Each edge now has a cost.
A cost. What does that mean in a graph?
Think of it like travel time between cities. Some routes are faster because of distance, traffic, whatever. Those things would be represented as weights on the edges.
So now it's not just finding a path, but the shortest or cheapest one.
You got it. That's where Dijkstra's algorithm comes in. It's a super powerful algorithm that factors in those edge weights when finding the shortest path.
So Dijkstra's algorithm is like a GPS on steroids.
Pretty much. GPS systems and network routing protocols use it all the time. But it's important to note, Dijkstra's algorithm doesn't work if there are negative weight cycles.
Negative weight cycles? What are those?
Imagine a loop in the graph where the total weight keeps decreasing as you go around it. It would be like time travel, arriving before you left.
Okay, that sounds like a problem.
Definitely messes things up. Luckily, most real-world graphs don't have that issue.
Okay, good.
So, Dijkstra's algorithm is a great tool, but got to use it in the right context. And that brings us to another concept, greedy algorithms, which are the focus of Chapter 8.
Greedy algorithms, what makes them greedy?
Well, they make choices based on what seems best right now, without looking at the big picture. Imagine someone at the grocery store just grabbing the most appealing thing in each aisle, not thinking about budget or nutrition.
So they're going for instant gratification without thinking long-term.
Exactly. Greedy algorithms don't always find the best solution, but they often find pretty good solutions quickly.
Quick and dirty.
Yeah, kind of. The book uses the knapsack problem to show this. Imagine a thief trying to maximize the value of stolen goods, but they have a weight limit for their knapsack.
Okay, so the greedy approach would be to just grab the most valuable things first.
Right, but that might mean missing out on a combo of less valuable items that would fit better and have a higher total value.
So sometimes being greedy can backfire.
Totally. And Chapter 8 talks about these things called NP-complete problems, which are notoriously hard to solve efficiently. They're like puzzles that get exponentially harder the bigger they get.
Even for powerful computers.
Even the best computers struggle to find the optimal solutions for big versions of these problems.
So what do you do then?
Well, for NP-complete problems, we often use approximation algorithms, like greedy algorithms. They try to find solutions that are good enough in a reasonable amount of time, even if they're not the absolute best.
So it's like finding a decent parking spot instead of circling for hours to find the absolute closest one.
Exactly. It's about balancing speed and accuracy. The chapter ends with the set covering problem, where you need to find the fewest radio stations to cover all the states in a region.
Okay, so the greedy approach would be to pick the station that covers the most uncovered states each time.
That's it. It might not find the absolute fewest stations, but it gets a good solution pretty quickly. Again, a trade-off.
I'm starting to see how algorithms are all about making smart choices based on the problem.
That's great. And that leads us to another powerful technique, dynamic programming. Chapter 9 focuses on this.
Dynamic programming, what's so dynamic about it?
It's all about breaking down a problem into smaller, overlapping subproblems and then storing the results so you don't have to redo the same calculations.
Oh, like building a Lego set by first making smaller parts and then putting them together.
Exactly. This can make things way more efficient, especially for problems where you need to do the same calculations many times.
Clever.
The chapter revisits the knapsack problem, showing how dynamic programming can find the best possible solution.
Really? So it can figure out the absolute best way to pack the knapsack.
Yeah. It does this by building a grid to track the maximum value you can get for different item combinations and knapsack sizes.
So it considers every possible combination.
Exactly. And by saving those calculations, it doesn't repeat work. It's a methodical way to guarantee the best knapsack solution.
Pretty neat.
What other problems can dynamic programming tackle? Well, the chapter brings up the longest common substring problem, which is about finding the longest sequence of characters that are in both of two different words in the same order.
Like finding the biggest overlap between two strings.
You got it. Dynamic programming solves this by building a grid that compares different substrings of the two words.
So it's like lining up the two words and looking for matching parts.
Exactly. And by storing the results of those comparisons, it avoids doing extra work and finds the longest common substring.
Efficient.
Dynamic programming is like a superpowered search and compare tool. It's great for optimizing solutions by breaking down complexity and avoiding unnecessary work.
This is all really interesting. I'm ready for Chapter 10, what's next in our algorithm journey.
Get ready to jump into machine learning with the K-nearest neighbors, KNN, algorithm.
Machine learning, wow, feels like we're entering a whole new world.
We are. KNN is a pretty simple but powerful algorithm that can be used for classification, grouping things into categories, and regression, predicting numerical values.
So it's like a computer learning to make decisions based on data.
That's a great way to put it. Like, imagine classifying fruit as an orange or a grapefruit based on size and color, or predicting how much someone will like a movie based on the ratings of similar people.
So the computer is basically looking for patterns and making predictions based on what it finds.
Exactly. Chapter 10 starts with that classic orange and grapefruit example, showing how KNN compares a new item to its closest neighbors, in a feature space.
So like looking at the surrounding fruits and guessing based on what they look like.
Good analogy. The chapter then goes into building a recommendation system with KNN. Imagine plotting users on a graph based on their movie preferences.
So people with similar taste would be grouped together.
Precisely. The algorithm can then recommend movies based on what those neighbors liked.
That's cool. But how does it know which users are similar?
It uses a distance formula to calculate how far apart two users are in terms of their preferences. The closer they are, the more likely they have similar tastes.
So it's like measuring distance on a map, but instead of physical distance, it's the difference in their movie choices.
Exactly. And the chapter also covers regression with KNN, where we're predicting a number, like a movie rating, based on the average rating of a user's nearest neighbors.
So like asking your friends with similar taste how much they liked a movie and using their average to guess your own rating.
That's a great way to think about it.
Yeah.
And Chapter 10 finishes by giving a peek into the broader world of machine learning, showing how KNN fits in, and introducing other algorithms like naive Bayes.
This is all so fascinating. Algorithms are used in so many parts of our lives, even if we don't realize it.
I know, it's amazing that they're behind the scenes, powering search engines, recommendations, even self-driving cars.
It's mind-blowing.
And we've got one more chapter to go. Chapter 11 takes us on a whirlwind tour of even more advanced algorithms and data structures. But before we jump into that, let's take a second to appreciate how far we've already come.
Yeah, for sure. We started with the basics of sorting and searching, and now we're talking about machine learning and AI. It's been quite a journey.
It really has. It's incredible to see how these basic concepts are building blocks for such powerful stuff.
I'm ready for more. Let's keep grokking. Okay, I'm ready. Chapter 11. What's next?
Well, it's like entering a secret library of advanced tools and techniques, right?
It's kind of exciting, but also a little overwhelming. Where do we even start?
Well, the book starts with trees, which are these hierarchical data structures that are really good for storing and finding information efficiently.
Trees. Like family trees.
Exactly. They branch out from a root node, and the data is organized in a structured way. Think about like file systems on your computer or databases. They often use a tree structure.
So instead of searching through everything randomly, it's organized to make finding stuff faster.
That's it. The hierarchical structure makes it super fast to find and retrieve data, which is super important when you're dealing with huge data sets.
Makes sense. What else is in this algorithmic library?
Next, we've got inverted indexes, which are like the heart of search engines.
Oh, wow, now we're talking. I use search engines all the time, but I have no idea how they actually work.
Imagine a massive table that connects words to the documents they appear in.
So if I search for, like, algorithm, the search engine uses this index to find all the pages with that word.
That's right. It's amazing how search engines can go through billions of web pages so quickly, and inverted indexes are a big part of that.
It's like having a librarian who can instantly tell you every book that contains a specific word.
Now, get ready for this. The Fourier Transform. It breaks signals down into their different frequencies.
Signals, like radio waves.
It could be radio waves, sound waves, light waves, any kind of signal that changes over time. The Fourier Transform breaks it down into its individual frequencies, like separating a smoothie into its ingredients.
That's a good analogy.
And it's used in so many fields: audio and image processing, compressing data, even analyzing DNA.
So it's like a tool for analyzing and messing with signals.
Okay, now let's talk about parallel algorithms. They use multiple processors to make computations faster.
So instead of one computer doing all the work, it's like a whole team of computers.
Exactly. Like having a bunch of workers tackling a job at the same time instead of one person doing it all. Super important for dealing with huge amounts of data or really complex calculations.
But I imagine coordinating all those computers can be tough.
You're right. It takes careful planning to divide the work, make sure the processors can talk to each other, and make sure the results are combined correctly.
Right, that makes sense.
Now, take that idea of parallel computing, but on a global scale that's MapReduce. a powerful algorithm for processing massive data sets that are spread across multiple machines.
Distributed, like the data's on different computers.
Exactly. It's like having a team of workers all over the world, each handling a part of the data and then contributing to the final result. MapReduce is used a lot in big data analytics, so we can analyze those huge data sets that wouldn't fit on one computer.
So how does it work?
It's a two-step process. Map divides the data and does something to each chunk. Then Reduce combines the results to get the final output.
It's like each worker analyzing part of a giant puzzle, and then they put their findings together to see the whole picture.
Good visualization. Okay, moving on, the book then gets into balloon filters and hyperlog, which are probabilistic data structures.
Probabilistic, does that mean they're not always right?
It means they give you an estimate, not an exact answer, but they use very little memory. They're like shortcuts that trade off a bit of accuracy to be super efficient with space when you have tons of data.
So for situations where you don't need to be perfectly accurate.
Exactly. Like a balloon filter can tell you if something is probably in a set, but it can't guarantee it's not there. They're used in spell checkers, spam filters, even to check if a search engine has already visited a web page.
Okay, that makes sense. And hyperlog.
It estimates how many unique items are in a set, like counting how many different species are in a rainforest without having to identify each one individually.
Wow, these data structures are really useful for managing all the data we have nowadays.
For sure. And next up, SHA algorithms, which are a family of secure hash functions used for keeping passwords safe and comparing files.
Hash functions. Didn't we talk about those with hash tables?
Yeah, but SHA algorithms are different. They're one-way, meaning it's easy to create a hash from the input, but practically impossible to go back the other way.
It's like a fingerprint. You can easily identify someone from their fingerprint, but you can't recreate the person from the fingerprint.
Exactly. That's why they're perfect for storing passwords securely. Even if someone steals the hash passwords, they can't figure out the original passwords.
That's good to know. Are there other kinds of hash functions?
Yeah, the book mentions locality-sensitive hashing, which tries to make hashes that are similar for similar items. This is how we find near duplicates in big data sets without having to compare everything.
So like grouping similar items based on their fingerprints?
Right. SimHash is one type that Google uses to find duplicate web pages, and Scribd uses it to prevent people from uploading copyrighted stuff.
Wow, that's really cool.
Okay, get ready for this. The Diffie-Hellman key exchange. It's a really elegant solution to a tricky problem.
Okay, I'm intrigued. What problem does it solve?
Imagine two people want to talk securely, but they haven't shared a secret key beforehand. It's like agreeing on a secret code without ever actually saying it directly.
That sounds impossible. How is that even possible?
Diffie-Hellman uses public and private keys. Think of the public key as a mailbox, and the private key is the key to that mailbox.
Okay, I'm following.
Anyone can put a message in the mailbox using the public key, but only the person with the private key can open it and read the message.
So like sending a message in a locked box that only the receiver can unlock.
Exactly. This algorithm totally changed how we communicate securely on the internet.
That's incredible.
Last stop on our algorithm tour, linear programming. It's a powerful way to optimize a system given certain limitations.
Optimizing. What does that mean here?
Think of it like figuring out the best way to allocate resources, like time or money, to maximize profit or minimize costs, all while staying within certain limits.
So finding that sweet spot that balances everything to get the best outcome.
Exactly. It's used in fields like economics, logistics, and even in designing efficient algorithms themselves. You define variables, constraints, and the objective you're trying to maximize or minimize.
And then it finds the best solution that fits those limitations.
Yep. Linear programming is a powerful way to make good decisions when you have constraints.
This chapter was packed with information.
I know, right? We've gone from basic sorting to machine learning to cryptography to optimization. It's amazing to see how broad this field really is.
It's a lot to take in, but I feel like I'm starting to get a better understanding of how these advanced algorithms work, and it's really fascinating.
It is, isn't it? And what's cool is that even though we've covered so much ground, we've really just scratched the surface of this vast and intricate world of algorithms.
There's always more to learn. It makes you wonder, what does all of this mean for us, for people like us who use technology every day? How can we actually apply this knowledge?
That's a great question. I think the biggest takeaway is that algorithms aren't just for like computer science people.
Right. They're not just for the super technical folks.
Yeah, they're for anyone who uses technology, which is basically everyone nowadays.
Pretty much, yeah.
And even beyond technology, like understanding how algorithms work can help us make better decisions, just in everyday life.
Yeah, it's like having a new set of mental tools for solving problems. It's all about breaking things down into smaller steps and figuring out the best way to get things done.
And it's not about memorizing specific algorithms or data structures.
Right. It's more about understanding the big ideas behind them.
Because once you get those fundamentals,
You can apply them to so many different things.
think of it like learning a new language.
Once you know the grammar and vocabulary.
I can say so many different things.
Exactly. So once you get the building blocks of algorithms,
You can use them to come up with solutions for all sorts of problems.
whether you're a programmer or a data scientist or just someone who wants to know how the digital world works.
Right. This knowledge is valuable for everyone.
It's about being able to think critically and creatively about all these challenges, in a world that's increasingly driven by algorithms.
So as we wrap up our algorithm adventure here,
I want to leave you with one last thing to think about.
okay, hit me.
We talked about how computers use algorithms to solve problems, right?
Right.
But did you know that our brains use algorithms too?
Oh, interesting.
Yeah, think about it. From recognizing faces to finding the quickest way to get somewhere.
We're basically running algorithms all the time without even thinking about it.
Exactly.
It's kind of mind-blowing that the same principles that power computers
Are also behind how our own minds work.
That's a great point.
Yeah.
Makes you wonder about the limits of algorithms.
For computers and for us.
Definitely.
Yeah.
And all the amazing possibilities that are still out there as we keep exploring this fascinating world of algorithms.
Absolutely. Well, thank you for joining us on this deep dive into the world of algorithms. We hope you enjoyed it and maybe learned a thing or two.
We had a great time, and we hope you feel inspired to keep exploring this amazing computational world.
Until next time, happy grokking.